Okay, hello, hello, hello. So I give a presentation on cross-chain arbitrage. That's, first of all, a joint project with a bunch of people at TU Munich, at Flashbots, at Lisbon University. And I link it a bit to questions of Ethereum interoperability. Okay. So, how are prices determined in sort of the current design of Ethereum, and how is the market structure currently? I mean, the general idea that people have is we have DEXs, but sort of price discovery is not really happening on DEXs, right? What is the reason? There is not as much liquidity as on CEXs, and there is sort of a delay, right? So you have not always a price determined at each point in time. So CEXs are faster, have deeper liquidity. So those two things are, of course, related to each other. And so we expect that more often new information is priced in a CEX rather than in a DEX, right? And then sort of the DEXs, they sync to the CEX, right? And then so you have sort of a price update to the external world off-chain. We could imagine a different world where we have price discovery sort of between DEXs, right? So you have different DEXs on different chains maybe, or different DEXs on the same chain, and they might also have different liquidity and different ways of making a market, but somehow the collective of those DEXs, they might eventually incorporate information in price hopefully, okay? So that would be another way of doing it. And that is actually not a hypothetical, but in some sense that is a reality, but sort of on the very niche of Ethereum or in the Ethereum ecosystem. So you have some situations where we have sort of price discovery on decentralized exchanges. And that is mostly very long tail kind of assets. And what we do in this project, we want to look at this long tail of assets, see how people arbitrage between them, between different DEXs on different domains, on different blockchains, L2s and L1s. And maybe that gives us an insight of how sort of a fragmented multi-chain world would look in the future. Or maybe it's just an interesting artifact. Maybe sort of we solve interoperability, maybe there will be one chain that will rule them all. We don't have the fragmentation, we don't have these problems of sort of syncing between different domains. And then maybe it was just a beautiful exercise to study a bunch of meme coins. So either way, I think it's cool. So what did we do? So we and by we I mean mostly Burak Öz is the leading driver on the data side of this project. We created a data set studying different chains, EVM chains, 9 in total, and we collected 1 year of data. And we tried to figure out situations that we could classify as cross-chain arbitrage. So one leg of the trade was done on one chain and the other leg of the trade was done on a different chain. Maybe there was bridging in between, or maybe people held inventory on both chains, but we sort of tried to match trades to the same entity on different chains. And that gives us a universe of considerable size, so you get 242,000 trades in total with, well, medium-sized volume, 868 million. And let us look at some nice graphs. So here's how it looks like. So we studied these eight different chains. And the period was from 2023 September to 2024 September. One nice thing is in between there was Cancun, which had sort of this nice effect that it decreased fees on Ethereum mainnet. So it made things arbitrageable that were too costly before that. That led to a certain spike in the activity on Ethereum, leading cross-domain arbitrage. Okay, so that's a data set. That's a volume, so around $3 million. I mean, in the total scheme of things, it might be little, right? If you think about more like other portions of MEV or arbitrage, but it's a considerable size data set, I think. So what can we tell about it? First of all, we've tried to correlate it with volume, and I think that is true for any kind of MEV extraction that it's more profitable on average if there is higher volatility, and there is a correlation between arbitrage volume and volatility. It's dampened a bit because those things are really, really, really long-tail things. What do I mean by long-tail? So why is price discovery happening on-chain rather than off-chain? Either they are not even listed on sexes, or there's just, that happens very often actually. There are things that are just don't have good liquidity or execution on a sex, right? So very, very low liquidity on a sex, and so we, people trade on DEXs primarily. What other things there? I mean, either the two classes basically, sort of meme coinish or very long tail experimental projects, right? With low market cap, and then low market cap synthetic assets like synthetic versions of dollars, synthetic versions of Bitcoin, and so on. So these are the top 10 tickers, I think. There's the Euro stablecoin. The Bitcoin is an aggregate of different sort of versions of Bitcoin. We have OmniCat, which is a cat token on OmniChain. We have the non-tradable token, like these kind of things, right? Okay. Non-playable token. Coin, NPC. Okay. So, how should we think about arbitrage extraction? So how is arbitrage extraction different if you have long tail assets? So first of all, there's a liquidity effect. I don't know whether you have heard about this entire discussion around lever, which is sort of prominent among professors, but maybe not so much in the community. So people have studied sort of the effect of slippage on arbitrage, right? And so you can adjust the standard theory of this effect of arbitrage, the slippage effect, right? The effect that there's limited liquidity on those DEXs, and so you basically get a smaller size arbitrage. So there's this shading factor, this x1 prime divided by x2 prime. So the relative fraction of the liquidity on the two venues matters for the amount of arbitrage. First of all, there's less of it, and it depends on the imbalance in liquidity. Okay, so that's how we think about it. But that's the liquidity cost, right? So the cost that there's limited liquidity, which makes arbitrage more costly. There are other costs, and primarily in our data sets, cost is cost of bridging, if you really do this arbitrage through bridging, using a bridge, or you have to maintain inventory. And if you have to maintain inventory on different domains for very long tail risky assets, that's very costly to you. So the one thing that we did on the theory side is we tried to have a very stylized model of this to try to have some kind of comparison between when does it pay off to bridge and when does it pay off to have inventory, right? Inventory trading is just this thing, right? So you maintain some, I don't know, NPC token on DEX on Arbitrum, and you maintain some NPC token on DEX on Ethereum, and you sell on the Arbitrum, and you buy on the Ethereum chain, right? That is instant settlement, almost instant settlement, right? There's maybe a difference in how fast those chains settle, but you have to maintain inventory. So it tends to be more costly for that thing, for that reason. If you do bridging, then basically what you have to do is you have the token, you trade it on Arbitrum, then you have to bridge it back to Ethereum using maybe native bridge or having some other kind of bridge solution, right? And then you trade it back. And doing that, time passes, right? It's a very long time to settlement, and you have price uncertainty. So it might be risky to do these kind of things. Okay. So that's the basic thing you have to think about in these kind of things. We have then a stylized model where you basically assume, okay, there sometimes just out of a sudden arbitrage opportunities arise, sort of through noise trading or for whatever reason somebody wants to trade these tokens, and they tend to sort of be quite, you know, they don't compensate for the risk in the sense that their price tends to drift negatively. Okay, so that is our model assumption. So it applies more like to this long tail assets than it applies to the synthetic assets. Okay, if you have that, then you can assume, okay, some arrival rate of those arbitrage opportunities, and then you can do some math around that. So you can think about, okay, If those arbitrage opportunities arrive more frequently, maybe it makes sense to maintain an inventory, right? But if those arbitrage frequency opportunities don't arrive that frequently, you might think about bridging it, because maybe the price doesn't move anyway too much, right? And there are less opportunity. Okay, benchmark is something like this. So if you have a very frictionless ideal world that I talked about before, also abstracting away from the liquidity effect, you have some profit function that is sort of this nicely convex shaped profit of arbitraging. Okay, but now we have a cost. It comes in two ways, and let me first of all talk about the bridging cost. So the bridging cost is first of all the cost of using that bridge, right? That costs you a fee, but also you have the price uncertainty. So the price might move against you while you're bridging, right? Quite naturally. Might also move in your favor, but it might move against you. And that introduces an implicit cost, right? The cost comes from the fact that once you've completed the bridge, basically your arbitrage opportunity might have disappeared, right? That is a risk. And you have to factor that in. So you basically get a sort of difference of two quadratics, and you get a cost that is increasing marginally in the time that you need to bridge the asset. Okay, that's plausible, I think, a plausible model of bridging. So let's compare that also to inventory. So what is the cost of inventory? It's basically the risk cost, or also the opportunity cost of holding NPC token or whatever token was in this data set, right? So you have an opportunity cost and you have a cost of, or risk of holding this asset. You might not be able to sell it, or you might not be eventually, or it might depreciate in value and so on. So basically you have a constant flow cost of holding this asset, right? So you keep it in inventory, and the flow cost always in each period, it is costly to hold the inventory. And then you have a nice trade-off, right? You have this formula where you basically compare sort of the expectation of this price depreciation of the token versus the frequency of arrivals of these arbitrage opportunities. And depending on this, you get sort of this mu divided by lambda formula, right? So the drift, so the price drift relative to the frequency of opportunity matters for the values that you incur. And then you have an inequality, then you compare, right? So in principle, we have a theory of inventory, whereas a bridge is sort of straightforward, tells you what you would expect it to tell you, right? The longer it takes to bridge, the more costly it is to bridge, the more you go for inventory. If inventory is very costly to hold because those things are volatile, or those things are depreciating in expectation, or they have very low liquidity, so you might not get rid of them, then you refrain from holding inventory. Okay, that's theory. How does it relate to empirics? And we've also looked into our data set. So first of all, there are really arbitrage, a substantial amount of arbitrage where people use bridges in arbitraging between these very long tail tokens. So they really takes this very long time to complete or finish the arbitrage. 242 milliseconds in median. And, you know, sort of inventory arbitrage by definition is almost immediate. 9 seconds settlement median. Did I say milliseconds before? Everything is seconds. Everything is slow in this project. Everything is slow, very slow. Okay. Majority, of course, is inventory. Or not of course, it happens to be. Approximately 2/3 in our data set is inventory-based arbitrage, and the rest, you have a bridging transaction in between. There is heterogeneity in bridging times and in bridging costs, and that also gives a heterogeneity in what people do, right? So there's a difference between native bridges in bridging time and these kind of other bridging solutions like wormhole, etc., where we have usually shorter bridging times. And, well, there's this sort of outlier. There was one searcher very prominently doing arbitrage on Ethereum and Polygon that gives this spike here in my data. Okay. So there's a division between inventory and native versus multi-chain bridging or non-native bridging solutions, I should rather say. So the majority were non-native bridging solutions, but some were done through the native bridge. Okay. So that's about this cost, and that reflects also in the way people arbitrage these things. Okay. How does the market look like? It's generally true, right, that searching or any form of arbitrage, there's this kind of Pareto distribution, right? So few people make all of the gains, sort of almost winner takes all game, right? Because of the basically skill factor involved in that to some degree. We also have this kind of basically few sort of stylized fact of few searchers extracting most of these arbitrage opportunities. So there are these top addresses that account for almost 50%, and then during Ding Kun, almost 75% of this total arbitrage volume. Okay. Final thing I wanted to do is link sort of these stylized facts and theoretical findings to the broader picture. So this is it's a niche, as I said, right? It's a niche. It's sort of a beautiful niche of beautiful, weird, long-tail tokens with funny names, and maybe we should ignore that. It's also like, I mean, for finance, proportion, it's not a large market. But there could be a potential world where we have fragmented liquidity, we have multiple chains, and cross-domain arbitrage will become more and more, increasingly more important, right? So there could be such world. On the other hand, I mean, tech tries to solve some of the frictions that I talked about. We should have maybe shorter bridges. We should have other interoperability solutions. We should have clever ways to route liquidity across different venues on different chains. So maybe we can reduce the friction and the cost in these kind of cross-chain markets, right? So those are the two forces. And I think one takeaway of the paper is, if we are in this hypothetical world where we have basically a lot of growth and a lot of fragmentation of liquidity, and sort of the technology doesn't follow that, I don't know which probability you assign to that world. I would assign to it a probability lower than 50%, but it's a possible world. Then you would have scale economies in searching. What is the reason? Because for this fact that there is a premium of having capital, right? So you can maintain inventory. There's a premium on being clever and managing risk. And all of these factors should be maybe a vector of centralization. Okay. But you can also take it as just sort of a documentation of a weird, beautiful world that might disappear in the future. Okay, advertisement, I promised to do. There are jobs at Flashbots, scan the bot. There's a preprint down there, you see all the authors. And there's another preprint for the theory folks in the audience that care about arbitrage calculations with Brownian motions. Those people might exist. But the other paper is more interesting, with a dinosaur, right? That contains all the data. I was 1 minute too fast.